everybody. Okay, so let me thank first of all the organizer of the school for inviting me to give this lecture. So it's a real pleasure. So last time that I was here, I was probably on your side. So okay, now it's quite strange to be on the other side of the chair. So I am Angelo Ricciardone. So as you probably know. So in this 5 lecture, I will introduce you to the stochastic background of gravitational waves. So with, let's say, an increasing way of difficulties of approaching the topics. So I will tell you now what are the outlines of the lectures. So how many of you knows or work on stochastic background? So just to have an idea. Okay, let's say more or less the 10% of you. Okay, so I hope that at the end of this lecture, of this 5 lecture, so at least half of you will learn something about stochastic background. In this way, we double the number of people that knows about stochastic background in all the world. Okay, so you more or less know how many people we are that work on the stochastic background. So in reality, so even if there are not so many experts on the topics, this is extremely interesting, as we will see, but it's also extremely challenging because detecting a stochastic background and characterizing a stochastic background, it's very hard. You will understand why. So let's start. So let me first of all give you the outline of the lectures. So first of all, I will introduce to gravitational waves. So during this first lecture, what I will do, I will connect gravitational wave sources, okay? And at this point, so I'm not still discussing, already discussing stochastic background. I will give an overview of all the sources of gravitational waves. So I will connect these sources to detectors. So what are the main detectors that are working now and will work in, let's say, more or less 10 years. And I will connect these to the difference frequency band, okay? Okay, in this way, so at the end of this lecture, you will have an overview of all the sources, resolved and not resolved sources of gravitational waves. What are the detectors that can detect them and in which frequency band they work, okay? So I hope that today I will be also able to tell you how gravitational waves emerge in GR, okay, in general relativity. So we will know how they derive as linearized perturbation of linearized solution of GR. So, and I will start introducing what is the stochastic gravitational wave background. Please tell me if you don't know any of these acronyms, okay? And I will characterize in sense that I will tell you what are the main observable quantities that we need to characterize the stochastic background. Then tomorrow I will describe a couple of cosmological sources of stochastic background, and also what probably you are more familiar, how to characterize an astrophysical background that is, as you know, probably is the counterpart, if you want, of the resolved sources detected by LIGO Virgo. Then on Thursday, So I will introduce you to the response, if you of a gravitational wave detector to a stochastic gravitational wave background, okay? And also I will derive what is the most known estimator for a stochastic background, that is the signal to noise ratio, okay? So the signal to noise ratio will tell us when a stochastic background is detectable or not in a first approach. Then finally, if I have time, no, I will have time, okay? On Friday, I will do something a bit more advanced for people that are knows a bit of statistics. Even if I will also give you the basics, I will tell you how to write a likelihood for a stochastic gravitational wave background. Okay, this is some things that you typically more or less don't find on the book, and I will introduce you to the simplest tool when you have detectors to understand the accuracy with which you can measure the parameters of your model, that is the Fisher matrix, okay? So this is more or less the plan of the lecture, okay? And if I have time, in the last part of Friday, I will tell you something about the stochastic gravitational wave background in connection with pulsar timing array that, as you know, in June has detected this collaboration, pulsar timing array collaboration, has detected for the first time, has claimed a detection of a stochastic background at more than 3-4 sigma, okay? But I don't know if we will succeed in doing this. So as Leonardo was saying yesterday, so I mainly work on cosmology with gravitational waves, okay, both for LISA and mainly for LISA and for Einstein telescope, and recently also a bit for LIGO Virgo, okay. Working on gravitation on cosmology for gravitational waves means also develop tools, if you want, to characterize the stochastic background, besides, let's say, trying to constrain cosmological parameters, as you probably are more familiar with. So, and in this lecture, you will understand why, let's say, the stochastic background tell us about cosmology, okay? Because probably it's not already clear. So of course, so if you have any questions, you can ask me during the lecture or in the office hour, and then also to Gabriele Perna, that will be the structure of these lectures. So this will be the content of the let's say theoretical lectures. So on the exercise part, what we have developed in reality is Gabriele mainly that develop everything. So we will give 3 theoretical, I would say, exercise, okay, among which the first one is mandatory, okay. And the first one, as you will see, is a kind of calculation that I skip during my first lecture today, and so you will know how to join these two parts. Then you have a second exercise that is on the computation of let's say the spectral energy density. So don't be scared, you will know what is it, for a source of a stochastic background from the early universe for scalar induced gravitational waves. And then there is a third exercise on the analytical computation of the response function, what is the response of my detectors to a stochastic background for LISA, okay? It's a bit more complicated than ground-based interferometer, L-shaped interferometers, but I'm sure that you will succeed in doing it. these two are, of course, you are free to do or not, but for your benefit, it's good to do. So, and you will realize this in 5-10 years. Okay. Then we have prepared three, for people that are familiar, Jupyter notebooks. Okay, so these Python notebooks that are focused on, the first one is on the computation of the power law sensitivity. That is the way in which we, let's say, qualitatively see, claim that a stochastic background is detectable. Then there is a second one that is the numerical counterpart of the computation of the response function, okay, because you cannot do it everything analytically for Lisa again. And the final one is related to this. It's a simple Jupyter notebook, depends from the point of view, simple, on the computation of the Fisher matrix for a stochastic background. So you will be able to say that when you will detect a stochastic background with the future detectors, or with the detectors in general, so you will know the accuracy that you are able to reach on measuring some parameters of your model. Okay. So this, I think, that covers more or less everything about the introduction. So let me give you the main references that I will use during these lectures. Okay. Okay. The first one is Michele Maggiore's book. So the size of my writing is fine or is too small? Is fine, because okay, I don't write very well. Michele Maggiore's book is the first volume, Gravitational Waves. Volume 1, okay, Theory and Experiment. Okay. Then we have the second one, that is again by Michele Maggiore, even if the first one is more important, is Astrophysics and Cosmology. Volume 2, Oxford again. Then we have a review by Chiara Caprini and Dani Figueroa. Okay, the title is Cosmological Background of Gravitational Waves. Okay, I give you the archive number, but it's published. Okay. Okay, then we have another review. Gravitational Waves from Inflation. Guzzetti et al. Okay. The archive is 1605 01615. Then you have a paper, okay, that is reconstructing the spectral shape of a stochastic background with Lisa. And it is 1906, okay, 092.44, okay. Then there is the volume 2 of this paper, that is the improved, is an extension of the first paper when you have 3 channels, when you consider 3 channels in the LISA detectors. Improved reconstruction of a stochastic gravitational wave background, again with LISA, okay. So the archive is 1906 09244, okay. Sorry? Okay, it's the same one, then I don't remember. Is I will tell you, yes, it should be. Okay, I don't remember the archive number. I will tell you later. Then I have science with space-based interferometer LISA, probing inflation with gravitational waves, and the archive number is 1610.06481, okay. And then you will have the review by Romano and Cornish, that is detection method for a stochastic gravitational wave background. Romano and Cornish. And the archive is 1608 06889, okay. So these are the main references for this course. So you have some review that are mainly focused on cosmological background. Tomorrow I will give you a couple that focus on the astrophysical ones. Then you have this paper that focus on the reconstruction of the stochastic background with LISA, and these are particularly important because they contain the tools that you will use in the exercise, essentially. Then you have this was one of the first papers that we developed in LISA, where we tell to the people that you can probe inflation with the gravitational wave interferometers. And then this contains essentially more technical details about how to detect a stochastic background, what are the challenges, and what are the main tools that are used in the community. Okay, so I will also give you other references when we will touch some other topics. So I will give you step by step. So, and what I need to tell you, okay, we will mainly use some conventions. Okay, we will, most of the time, not always, so don't complain too much when okay, this is the signature that we will use. Okay. And H naught. Okay, you should have everything that you need to follow these 5 lectures. Yes. Huh? So you will see when we will introduce the inflationary setup. Okay, it's just a convention to rescale the Planck mass. Okay, so it's that because sometimes I use the capital one, sometimes I use the small one. Any questions or curiosity? Can I? Okay, so let's start. As I was saying, I will start with an increasing level of knowledge. So let's start with a, let's say, short historical introduction to gravitational waves. Don't tell to LIGO Virgo people that I summarize all the work on gravitational waves in 5 items, okay? So, because there is a lot of efforts behind. So gravitational waves, as you know, uh, were predicted in 1916 by Albert Einstein, linearizing his equation. So the first indirect detection of gravitational waves happens in 1964, okay, when Hals and Taylor detected the pulsar how is it? PSR 1916-13. Okay, so this was the first indirect detection of gravitational waves, because what happens was that these two guys, so essentially were looking at the orbital period of these two pulsar, and they were measuring that essentially, let's say that is this the orbital period, it's not real the orbital period, these are the years, okay? So, and they were measuring, okay, that this orbital period decays, okay? So, and if you do the computation of this orbital period using GR, so you will see that GR perfectly fits the behavior of the orbital period, and this was one of the first confirmation of the evidence of the correctness of general relativity. It was perfectly able to reproduce this decaying of the orbital period. Then after this, so they won the Nobel Prize in 1993 for this discovery. So essentially, these were two neutron stars, two pulsars that were rotating among themselves, as we will see, and they were losing, let's say, the period. They were losing period because there was an emission of gravitational waves. Okay, so and the rate of emission of gravitational waves was in perfect agreement with the calculation done in GR. So then I would say that the next step after many years of technological development happens in the 2015, when the LIGO Virgo Kagra, at that time was just LIGO and a bit of Virgo, first detect directly. I will tell you what means gravitational waves from a compact binary system. Okay. So this was a big revolution because, as you know, first of all, we had the first direct detection that gravitational waves exist. Probably this one is one of the strongest confirmation uh, of general relativity. Uh, and then, as you know, it had a lot of implication both for astrophysics but also for cosmology. Okay, then we discovered that gravitational waves coming from these gravitational waves were coming from emerging of two black holes of around 30 solar masses. So, and today, after 8 years, more or less, so we have around 100 detected events. 98% are binary black holes, gravitational waves coming from binary black holes. A couple of them comes from the merging of two neutron stars, and there is one that is probably coming from the merging between the neutron stars and the black holes. Okay. Then I think that was the 2019 where where yes, no, 2017. Sorry, when Weiss, Barish, and Thor won the Nobel Prize, okay, for their contribution to the detection of gravitational waves, okay. So, and finally, I would mention the 2023, June 2023, when there is the first claim of detection of a stochastic background from PTA, collaboration, okay? Pulsar timing array, okay. So I think that this concludes the, let's say, the historical overview. So let's now go to a bit more, but still qualitative introduction to gravitational waves. So I want to give you just a, let's say, an analogy of gravitational waves to understand for people that are less familiar what they are. Okay, so so essentially, if you want, gravitational waves emerge quite naturally in GR, as we will see later. Okay, as soon as you linearize your Einstein equation. So, and they are propagating oscillations of the space-time metric or if you want of the gravitational field. So in the same way, just to give you an idea, as electromagnetic waves are propagating oscillation of the electromagnetic field. Okay, so this is a very easy, how to say, qualitative way to describe gravitational waves. In the later, I will give you more quantitative definition of a gravitational waves. So if you want to have let's say an idea in your mind. So let's think about the electromagnetic spectrum, okay? So the electromagnetic spectrum goes from frequency from 10 to the 4 hertz, okay? So in the radio, up to 10 to 20 hertz for gamma rays, okay? So if you want to stress again this analogy, so you can think about the gravitational wave spectrum from 10 to minus 18, 17 hertz, let's say, up to few years ago, I would say 10 to the 4 hertz, okay? Now, as I will tell you later, there is a lot of efforts in pushing this boundary up to, let's say, 10 to the 9 hertz, okay? What is called the high frequency regime of gravitational waves, okay? And here we go from CMB scale, for people that are familiar cosmic microwave background. As you will see, this was the first probe to detect gravitational waves along the years through the B modes polarization of the CMB, up to frequency coming from merging of compact object, okay? So I'm still talking about, yes, I still not introduce what is a stochastic background. Okay, so this is just an analogy to tell you how to think about gravitational waves. So now the first part of the lecture will be devoted in taking this spectrum of gravitational waves in frequency, okay, starting from CMB frequency, going up. I will not discuss high frequency, please. So if you compute the frequency that corresponds to modes, yes, that enters, yes, it corresponds to 10 to minus 18 hertz, up to 10 to the 4 hertz, okay? So we'll take this, yes, please. Okay, to this frequency spectrum, I will divide it, okay, in different frequency range, okay, and I will tell you mainly in four in four frequency band, okay. So the first frequency band is what we call high frequency band, okay. So this is high frequency band. So when Kip Thorne decided this nomenclature, so the high frequency community was not active, the one that goes from 10 to the 4 up to 10 to the 9 hertz. So this is still, if you want, the frequency band between 1 and 10 to the 4 hertz, okay? So when I talk about high frequency, I mean this, I don't mean beyond. So then we will have what I call the low frequency band. That goes from 10 to minus 4, let's say, up to 1 hertz. I am a bit optimistic this morning, 1 hertz. Okay, we will not reach with 1 hertz. Then we will have the third frequency band, that is the very low frequency band. That is between 10 to minus 9 and 10 to minus 7 hertz. Okay. Yes. And then you have the final one, extremely low frequency band, that is ELFB. that is between 10 to minus 18 hertz and 10 to minus 16 hertz, okay? Okay, of course, this is not a nomenclature, a definition that is set in stones. So it's a way that I want to tell you what are the main frequency band that where there are already detectors, or there are detectors that are planned, okay, for the next future. Of course, there are, if you see, there are some gaps, for instance, as we will see soon, that in which still the community is trying to push for building detectors. Okay, so everything is clear. Okay, now what I will tell you is just for a general knowledge. So I will tell you what are the sources in all this frequency band, and what are the detectors that are planned to work in this frequency band. So at the end of the school, you know some sources and some detectors. So let's start from the high frequency band. Okay. So the high frequency band is, if you want, the frequency band of ground-based interferometer. Okay. So when I talk about ground-based interferometers, okay, let me first tell you why ground-based interferometers work in this frequency band. Okay, so the lower bound, the 1 hertz, if you want, is a limitation from essentially seismic noise. Okay, so on the Earth, you are not able to go below 1 hertz because you are limited from the seismic or the Newtonian noise if you want. Okay, so to go below, you have to go in the space, as we will see, and as we will go. The upper bound, 10 to the 4 hertz, is mainly limited is due to the quantum noise, mainly, okay, of your laser. Okay, so this is the reason why you are limited in this frequency band, and this gives you the, let's say, the boundary of this frequency band. So what are the detectors that works in this frequency band? Okay, so at the moment we have LIGO, the two LIGO in Hanford and Livingston. Okay, they are two L-shaped interferometers. Okay, one with 4-kilometer arms. Okay, yes, and so they are two in US. Okay, and they are separated by 3,000 kilometers. Okay, L shape means that. So this is the shape of the detector. Is a Michelson interferometer with an L shape. Okay. So then we have a close interferometers, Virgo in Cascina. Okay, close to Pisa. Okay. This is again an L-shaped interferometers with 3-kilometer arms. Okay, it's not 4, it's 3. So then we have Kagra in Japan. Okay, it's again an L-shaped interferometers with 3 kilometer. The only things of Kagra that differentiate between the LIGO and Virgo is that it has a cryogenic technologies that allows you to push the low frequency part of the spectrum. Then, okay, less known is Geo 600. Is an interferometer that is in Germany. Okay, it's mainly a testing interferometers with an L shape of 600 meters. Okay, and these are all second generation interferometers, more or less. Now let me tell you about third generation interferometers, what we will have in the future. So remember that between the future and the present, the life goes on. So there will be intermediate step between, let's say, LIGO Virgo and okay, I don't cancel here, I just remove. And what will be the third generation interferometers that are Einstein telescope, okay, ET, and Cosmic Explorer. So there will be upgrade version. Sorry? Is Geo 600. Is a small detector. Yes. Yes, it's a detector that is in Germany. So it's essentially a probe for testing the technologies that are applied to LIGO Virgo. Okay. So so these are third generation interferometers. Why they are called third generation interferometers? Because in principle, they should push the sensitivity down at least of 1 order of magnitude compared to the actual one, and eventually even better. Okay, so what is let's say the planned version of Einstein telescope, at least up to 2 months ago? It's a triangular interferometers with 10 kilometers arm. Okay, so essentially triangular means that they are 3 interferometers. Okay, that's the advantage, some disadvantage that I will not discuss, of a triangular interferometers with 10 kilometer arms. Okay. Again, also Einstein telescope will have a, let's say, cryogenic technology to push, first of all, the low frequency part of the band, and also we'll have, compared to LIGO Virgo, a larger frequency band, trying to push also the high frequency part. Okay, so and the candidate site for Einstein telescope are Sardinia and let's say Netherlands, even if it's not exactly, is in a corner between Netherlands and Germany. Okay. Okay, so these are the two candidate sites. We are still discussing in the community if it's better a triangle or two L interferometers with 15 kilometer arms. Okay, separated by some distance. So this is a discussion going on in the community. Then we have Cosmic Explorer. Cosmic Explorer, as you can imagine, is the advanced version of LIGO. There should be 2 interferometers, one of 40 kilometers and one of 20 kilometers. Sorry, okay. One in US and the other one in Australia, okay. Okay. And this, I think, that close the panoramic of the ground-based detectors. So now let's go and see what are the sources that you expect to see in this frequency band. Okay. So yeah, it's still in between 1 and 10 to the 4 hertz. Yeah, okay. So sources in high frequency band. Okay. So mainly they are compact object. So this means black holes, binary black holes, binary neutron stars, and black holes, neutron stars. Okay. Then you have yes, stellar collapse to a black hole or neutron star. So essentially you have supernova. Okay, sources. Okay. So this compact object, when I mean compact object, I mean with masses that are below 10 to the 3 solar mass, okay? And yes, that's these are the main sources. So don't worry. So these are resolved sources. I'm still not introducing the stochastic background. So we will, the main lecture, the main topic of the lecture is stochastic background. But for the moment, so so consider this, because these are sources that appear as a transient event in this frequency band, while the stochastic background is something that permeates our universe, so is more or less everywhere. Okay, so then just to tell you, so there is these efforts in the very high frequency, let's call it very high frequency community, where you have different kind of detectors. You don't rely anymore on, let's say, interferometers, more or less, even if there are some version. And you try, there are different kind of detectors, like haloscopes, like levitated sensors. There are different technologies. So, and these are mainly developed to detect or some neutron stars, okay, events, or even better, some cosmological sources, okay, stochastic. I will not tell you why, where, which one, okay, but if you are interested, please ask me. Okay, so let's move now to the low frequency, okay. Okay, low frequency band. So this is the territory of space-based interferometer. What are the main, okay, the main limitation for these interferometers? So consider that the main source of error for of uncertainties for this interferometer is the laser noise, okay? So you have the laser noise always there, okay? People, what has done is introduce what is called the time delay interferometers to reduce this source of uncertainties, okay? So assuming that you are very nice and you are able to perfectly do the TDI, okay? So there are two main sources of noise, okay? The low frequency, okay? The low frequency part, the 10 to the minus 4, 10 to the minus 5 boundary is set by the acceleration noise, what is called acceleration noise of test masses. Okay, while the upper part, let me write 10 to minus 1 or 1, okay, is the displacement noise, also called interferometric noise. Display. Okay, so why I introduce test masses? Because the technologies for space-based interferometer is a bit different. So to understand this, let's consider that, let's say, the main mission for the space is the laser interferometer space antenna. Okay, is LISA. Okay, this is a gigantic interferometers in the space. Okay, it's still a triangular detectors made of 3 spacecraft. Okay, where in this 3 spacecraft separated by arms that are 2.5 million kilometers. So you can understand the level of complication. So each arm is 2.5 million kilometers. And in each of these, I simplified the stuff. In each of these spacecraft, there are some test masses that are free falling. Okay. So you can imagine then what are the acceleration noise in the low frequency and the displacement noise. So essentially there are source of noise due to the uncertainties on the measurement of the test masses that are in free falling. Okay, so LISA has been adopted 1 month ago, so we are very happy that ESA and NASA will develop LISA and for sure. Okay, now we are working on the uh, on the let's say the science target. Okay, then the second detector in space is Taiji. Is the, let's say, a Chinese interferometer similar to LISA, again triangular, but 3 million kilometer arm. So the technology is the same, more or less the same. Okay. So then we will have BBO. Okay. Okay. Let me no. Then we will have this IGO. These are all planned. Okay. No one of these is already active. Okay, is again a triangular interferometers, but with 1,000 kilometers. And then you have BBO, Big Bang Observer, that is a David stars interferometers in the first version, plus two triangle in the advanced version. Okay, and these are with arms of 50,000 kilometer. Okay, this should cover. Okay, then there is Tianguin, that is another Chinese interferometers, but yes, I will not discuss it. Okay, so triangular again means that it's more than one. Okay, we will understand better in the theoretical part and also in Gabriele's exercise. Okay, so what are the main sources active in this frequency band? Okay, so I think that I am a lot behind. Okay, so the main sources are galactic binaries. So these are mainly white dwarfs in our galaxy. Okay, so I will tell you what they look like later. So then there are massive black hole with mass larger than 10 to the 4, but from, let's say, 100 up to 10 to the 8 solar masses. Okay, so then you have the in spiral part of stellar origin black hole binaries. Okay, these are essentially the LIGO Virgo sources, some of them that in the spiral phase we will show up in the LISA frequency band. Okay, so these are okay, solar mass black holes. And then we have also what are called extreme mass ratio in spirals, or MRIs for the friend, that are essentially what they are. So they are intermediate mass black holes. Okay, so with masses in this frequency band that rotate around a very massive black hole. Okay, so and they have an extremely complicated dynamics. Okay, so this I think that is the part of the low frequency band for space-based interferometers. So now let's go to the very low frequency band. So the VLF, that is between 10 to minus 7 and 10 to minus 9 hertz. Okay, so in this frequency band, so the technology is a bit different. So pulsar timing array. Okay. So what they are? So they are the Parker pulsar timing array. Okay. European pulsar timing array, nanograph, and Chinese pulsar timing array. So they are different collaboration that goes all together in the pulsar timing array collaboration that claim this detection of a stochastic background. So just to go a bit faster, so what is the physics behind the detection of a stochastic background? So they use millisecond pulsar, okay? So, and essentially what they measure is the time shift between the observed time of arrival of the pulsar and what is the model of your time of arrival, okay? So we will do this in the last lecture. So if you measure this time shift and it happens to be, let's say, naively different than 0, then there should be something between the pulsar and yourself, okay? So, and if there is something between the pulsar of yourself that respects what is called the Ellings-Downs response of, that is a quadrupolar, let's say, response of your detectors to something, okay? This is the detection, this you can claim a detection of a stochastic gravitational wave background, okay? So, and this is essentially the way in which they detect gravitational waves. Finally, let's go to the final frequency band. So, and let's change even more the strategy. Okay, there is more noise than okay. No, there is a lot of more. Yes, there is problem of noise. There is problem of calibration. There is problem of systematics due to calibration, due to the motion of the earth, to the ephemerides, and so on and so forth. So I will, if you want, I give you an idea of this boundary. Okay, so the boundary of this frequency band. Okay, besides all the source of uncertainties are the following. Okay, so the 10 to minus 7 is essentially averaging over several months to reach the required level of accuracy. So if you integrate over several months of accuracy, so you need this boundary. You cannot go below, at least if you don't increase the number of data. Consider that now we have 20 years of data, if I'm not wrong. And then the 10 to minus 9, okay, boundary is due to the fact that these are millisecond pulsar, okay, essentially, and you're observing them for 40 years. It's 40 years that we observe this object. So this sets the boundary. So the accuracy that you want to reach and the number of years of observation. But besides these limits, there is a lot of uncertainties. What I write this T model, it's a complicated stuff that we will see on Friday. Okay. Okay. Then extremely low frequency band. So for people that have passions about cosmic microwave background, this is the territory, the band related to the, okay, between 10 to minus 15 and 10 to minus 18 hertz. Okay, it will be clear when I will explain the cosmological sources, this frequency band. So this is the territory of cosmic microwave background. Let's call it experiments, even if they are not really experiments. Okay, CMB, well, let's call it experiments, okay? Okay, so these bands is mainly related to cosmological sources, So there are no astrophysical sources there. Ah, sorry, I forgot to tell you the sources here. Sorry. The sources, as you can imagine, are supermassive black hole binaries, okay? Uh, uh, with, with masses that are above 10 to the 11 solar masses, okay? These are the sources here. So, however, there is a long discussion in the community about both the existence of these so large black holes, okay, and also about accounting for the latest data on how the expected frequency shape of this supermassive black hole fits the data. So, also there are many cosmological sources, and we will see together what they are, okay, that appears in this frequency band. Okay. Then finally, as I was saying, this frequency band is mainly for cosmological sources. Okay. Mainly, if I would say, inflation, if you want. So. Okay, so it's better to describe these sources instead of working in frequency to work with wavelengths, and these wavelengths that enters in this frequency band are between 10 to the minus h naught to the minus 1, lambda h naught to the minus 1. So essentially they are the modes that are within the horizon today, and that enters after the equality. Okay, this is the range of scales for these modes. This is h to the minus 1 is the Hubble is the horizon essentially today. Okay, so these waves, if you want, they oscillate with a wavelength that is comparable to the sides of our universe. Okay, so this is the wavelengths of these modes. That is also to reply to your questions. Uh, what is very important for these kind of signals is that if we will be measure if we will measure these gravitational signals, so these primordial, what are called primordial gravitational waves, so they have an amplitude, a root mean square amplitudes that is proportional to the energy scale of inflation over the mass Planck, okay, square. So as soon as we will measure these primordial gravitational waves, we will know the scales, the energy, if you want, at which inflation happened. Okay. So of course, there has been a lot of work also in the CMB community. Okay. The latest, I would say, constraints come from Planck, the Planck satellite. Okay, in combination with the BICEP plus keck, okay, plus, if I'm not wrong, with LVK, okay, okay, LIGO Virgo Cagra. So the way in which these are constrained, sorry if it changed a bit because I didn't introduce you what is the tensor to scalar ratio, okay, but if you are familiar with it, this is the ratio between the tensor power spectrum and the scalar power spectrum, okay. So if you combine all this data, you should get something that is 0.03. Okay, this is a bound. Okay, sorry. Okay. Yes, it's the scalar power spectrum. Yes, this is the tensor and this is the scalar. So this is one of the latest constraint combining these. Okay. Then we will have a forecast for the future. Okay, we will have Lightbird that should push these limits at least one order of magnitude less, and also CMB stage 4 is another experiment that should have more or less the same level of accuracy. Okay, and as you can understand, more we set stringent bounds on these, more we set limits on the energy scale of inflation. So, but now, of course, you are worried because you say, okay, I came here to learn about stochastic background, and this guy is talking about resolved sources of gravitational wave. So this is a bit crazy. That's not true, because so beyond all the sources that I discuss now, so there is something that is everywhere, okay? That is the stochastic background of gravitational waves. So what is this stochastic background of gravitational waves? So it's an incoherent superposition, okay? Of gravitational wave sources that are not resolved, not in time. I will give you a better definition later, nor in the angular domain, okay? Okay, so this is the definition of a stochastic background. So before I discuss, except for the CMB part, I discuss all resolved sources, everything that is transient in your detectors on which you can do the match filtering with your waveform. Now let's discuss, this is a bit more complicated, okay? To understand this, you should think about the two main sources of stochastic background, that is the astrophysical background and the cosmological background, okay? So these are the two main contribution to the stochastic background, okay? So to understand the astrophysical background, that is easier, if you want, to understand. So imagine that you have your detectors, okay, whatever it is, an L-shaped detectors, and you are here, okay? So you look back in your universe, in the light cones, okay? So as you know, and you see all your black holes, and so on and so forth, a lot of black holes. So, but as you know, your detectors will have a limited, if you want, resolution in which you can distinguish this source as resolved, okay? So all this band, in all this, up to this distance, if you want, your detector, this is just to give you an idea, we resolve all the sources. So it will see the source in the sky, and it will pinpoint one by one, okay? But at some point, the resolution of your detector is limited, so but you still have a lot of sources back far in our universe, and this due to limitation of the detectors, are perceived as a stochastic background, right? It's an incoherent superposition of sources that you are not to resolve anymore, okay? This is the simple way to think about an astrophysical background. But in the case of the cosmological case, where all these sources comes from the early universe, okay, the situation is a bit different, because you can even think in this way, taking your universe, computing the number of patches in your universe, and see that they are a lot, and this seems to overlap. But the situation is more simple than that, because all the cosmological gravitational waves, they comes from quantum fluctuation. Okay? Okay? They come from quantum fluctuation. And if they are quantum, they are stochastic. Okay. So this is the simplest way to think about the cosmological case. And if you want to characterize a stochastic quantity, so you need to work with the statistics. You need to work with what are called ensemble averages, okay? So you need to work, for instance, with 2-point correlation. We will see what they are, okay? So, but this is the way to characterize. So comparing, so if you want to do a comparison, okay, for people that are in the field, so when you have your resolved sources, you take your waveform, okay, that you measure, okay, your data that you measure, you match this waveform with the templates that have been developed by smart people in the past. And if the two matches, this is very naive, okay? You are saying that there is a gravitational wave passing in your interferometers. In our case, for the stochastic background, this guy is 0, okay? So you cannot take your waveform, if you want, and do the matching, because there is no waveform for the stochastic background, because the stochastic background, if you look in your detectors, look like a noise, okay? So it's a very, it's a kind of white noise in your detectors. So this means that if you want to start looking and characterizing the stochastic background, you have to take two, if you want, mode function. We will tell you what they are, the amplitudes of the stochastic background, and take the 2-point function, where these symbols means that we are doing an ensemble averages. And then I will tell you how we will manage with these ensemble averages. But I stop at 45, right? But let's see where these gravitational waves comes from. Yes, please. That's a very good question. So at the end of the day, so what you will measure, so is a combination of the two, okay? So, but there is one important clarification to do. While for the astrophysical case, at least for the sources that we know, I'm not discussing about some exotic sources like boson stars and so on. So you know more or less the frequency shape, okay? So you know the frequency shape. We will see why the frequency shape is this, okay? For the cosmological one, it's model dependent, okay? So you can have whatever you want, because as we will see, I will list you the main sources for cosmological background, but it's model dependent, okay? So at the end of the day, when you will measure your data, you will have the signal plus the noise. In this signal, you have everything. But for the astrophysical case, since at least for the binary black holes, we have some indication from LIGO Virgo, okay, we more or less know the expected amplitudes in the other frequency band, okay? We can extrapolate this. But whenever you will measure the stochastic background, you will measure everything together. So you will have to develop tools to separate the two, okay? Because you will measure everything together, but on top of this, there will be the cosmological one, hopefully. So we will have to develop tools to distinguish the two. And I will tell you in these lectures what are the tools that we have developed to distinguish these two, okay? So this is omega. You don't know what is it still, but you will know. Okay, so at the end of the day, so you have upper bound, and I will mention if you want. On these, okay, since you ask, is good. So essentially, I did the 20% of the lecture that I was planning to do. I hope that at least is clear. So let's mention what are the cosmological sources and what are the astrophysical ones, okay? So the main cosmological sources are the following. How many people are familiar with cosmological sources of gravitational waves? 0. Okay, very good. 1, 2, 3. Okay, So the most known, of one of the most studies, are inflationary gravitational waves. Okay, this is okay. So these are gravitational waves coming from an accelerated period during the early universe that, amongst the many benefits, allows to stretch the scalar and tensor perturbation on super horizon scales. So, and this uh, uh, will can be potentially detected by gravitational waves interferometers. So the second source that is still related to inflation, but there are some extension. Let me call it extension of inflationary scenarios. Okay, so I will tell you why I need to introduce some extension of inflationary gravitational waves. Okay, then we have phase transition in the early universe. Not all the phase transition, first order phase transition in the early universe. Okay, then I have topological defect, and in particular cosmic strings. Okay, still in the early universe as a remnant of first order phase transition. Then we have another source that in the recent years becomes very popular, that are gravitational waves induced by scalar, and recently people discover also by tensor. So you will get lost, but I tell you, perturbation. Okay, let me explain you a bit more about this. Okay, so essentially, I don't need to explain because I will compute this guy. Okay, so these are the main cosmological sources for gravitational waves interferometers. Okay, the one that I measured before. At least cosmological, there could be other ones, but these are the main one. So we will look in details these. I will do the computation for this. We will look to this. We will do an extension to see what means extension. And I will tell you about these gravitational waves induced by scalar perturbation and understand why they became so popular. So just a spoiler, because they are related to primordial black holes. Okay, that's the reason why they became very popular. And among all of them is the only one that we are sure that they exist. Okay. So let me also mention at this point what are the main astrophysical sources for the background. Astrophysical gravitational wave background sources. Okay. Okay. So in principle, all the ones that I measure up to now. Okay. Because at some point the resolution of your detector is limited. So all the sources, massive, solar mass, massive, supermassive, and so on, can become a stochastic background from your detector. But in principle, so you can have detectors that are better than other detectors. So it should be, in principle, this classification should be, let's say, detector dependent. Okay, I will not touch in details these, but I will give you the guaranteed stochastic astrophysical background for some detectors. Some things that we know that at some point when we will switch on the detectors, they will show in the data. Okay, for sure. So I'm talking about LISA. Okay, in LISA there will be two guaranteed sources of stochastic background. One are the galactic binaries. okay? All the white dwarfs in our galaxies, okay? Consider that they are something like 10 to the 6, okay? So all on the galactic plane of our galaxy. So as soon as we will detect, we'll, we will switch on LISA, so we will see this in the data. So again, you need to subtract this guy to do the analysis. Then what you have, again, guaranteed in LISA, is the stellar origin black hole binaries, okay? So these are essentially the guys that LIGO Virgo detected, okay? So in principle, what happens is that, okay, I still didn't introduce uh, LISA and LIGO, but imagine that these are the noise of the two detectors, okay? Okay, let's do it this way. What happens is that according to the bound on the merger rate given by LIGO Virgo, so we expect that these guys that merge in the LIGO band will in spiral what is in the LISA band. So since we have many of them, according to the merger rate bounds, so this will form a stochastic background, okay, in the LISA band, while we will resolve in the LIGO band. Then on top of this, people think that also the M rays can form a stochastic background, okay, but still there are estimates for this, for LISA, okay. And then going beyond LISA, if you want, I would say from PTA, okay, there is a stochastic background generated by supermassive black hole binaries that, if you want, is one of the potential sources detected by PTA. Okay, so these are the main astrophysical sources. Yeah, extreme mass ratio in spiral. There are these small object, black holes, that gravitates around a large object, so and they merge at some point and generate gravitational waves. So people are estimated the number of expected sources in the LISA band, and there are some claim that it can form a very small stochastic background. Yes. Okay, that's good. So it depends from the point of view, of course. And okay, they can be both a stochastic background. Okay, when I will do the when I will do the derivation for the astrophysical background, and we will see how it behaves as this f to the 2/3. Okay, I will also mention the behavior of the primordial black holes background. That essentially is dictated, if you want, okay, by the dynamics, but also from the merger rate of these guys that is different from the astrophysical one. But in principle, they can both be some of the resolved sources measured by LIGO, at least the low mass ones, and also the stochastic background, but is there. Okay, so what I mentioned here is the guaranteed one. Something that you are sure that you will switch on your detector and you will see. So I skip, of course, there are bounds on this because people have tried to measure this. We have not detected except for PTA. And but there are, so this means that if we have not detected, we have bounds on what is the spectral energy density of gravitational waves. So I will not mention them. I will skip this part. Okay, but we have bounds on the amplitude of this guy. So in this remaining 50 minutes, so there are two options. Or I start introducing you how gravitational waves emerge in GR, but for sure I will not finish. Okay, okay, and or I introduce what Gabriele will tell you about, but probably I do the first thing. So, and then you will introduce them, and I will finish tomorrow. Oh, of course, okay. So, okay. So how gravitational waves emerge in GR? So let's start doing a bit of mathematics. Okay, so first of all, we need to quantitatively define gravitational waves. Okay, because at the moment I was quite qualitative. Okay, so if you want to define gravitational waves in a quantitative, more accurate way, so these are radiative. Okay, let me take the definition properly. And gauge invariant tensor perturbation of the space-time metric. Okay. So if someone asks you at the exam what are gravitational waves, this is the way to define gravitational waves. So I underline two words because these are the most important. Okay. So what means radiate? Is there any questions? No. So what means radiative? So radiative means that they propagate like waves. Okay. So they have they respect a wave equation, as we will derive this, both in the absence of a source and in the presence of a source. So let me write just now in this way. Okay. And what means that they are gauge invariant? This is more important. So for people that are not familiar with gauge transformation, so if you can define the gauge invariance as independence from the system of coordinates that you choose. Okay? So these are the way. So then this is the way to classify gravitational waves. The first, to understand how they derive, let's start from the flat space-time case. Okay? So this is the easiest way to introduce gravitational waves in the flat space-time. So at the end of the day, what you will do, so later, okay, we will extend these to the case of curved space-time, but for the moment, let's start from the flat space-time, okay? And as you know, these gravitational waves will be solution of the Einstein equation, okay? So let's start from, the flat space-time metric, okay? That is Minkowski plus a small perturbation, okay? You have your flat space-time, okay? Where you have the background matrix, and then you add a small perturbation on top. So, and this, we will see what these guys are. So, the first thing that you have to assume when you want to linearize your Einstein equation, okay? So you have to work in the weak field approximation. So you have to assume that this guy is very small, okay? So, but as you know, and these gravitational waves, as I was saying, they have to be solution of your Einstein equation, okay? So, but as you learn in your GR course, so GR, okay, is invariant under diffeomorphism, okay? Okay, so assume that your diffeomorphism phi, that is the link between your manifold, your, let's say, system coordinates is not properly right. So, okay, so this means that if I am in a system of coordinates and I move in another system of coordinates, okay, this will be given by this change of coordinates, okay? So, and this is, let's say, my diffeomorphism. Okay, saying that, so GR must be invariant under that. So to understand this, let's look at how my metric tensor uh, uh, behaves, okay, under this coordinates transformation. It should be okay, or I mix the indices. Okay. Yes, sure. Okay. This is G mu nu prime of X prime, okay? So this is the way in which your metric tensor transform under a coordinate transformation. So the fact that we are able to choose this diffeomorphism, okay, means that we have some gauge freedom, okay? This is a very important condition to arrive at the final degrees of freedom. Okay, so if you now look at how your metric perturbation transform under diffeomorphism, under this transformation, you will realize that H prime mu nu of X prime mu, you just do this, you apply this formula, okay? This minus the Lie derivative of H mu nu, okay? So where the Lie derivatives along the vectors is defined as d mu psi nu, okay? There is a 2 here, okay? So, and if you do this, you realize that this will be equal to H mu nu minus d mu xi nu minus the nu xi mu, okay? This is the way in which they transform. You still have to impose the weak field approximation, okay? This means that this guy must still be smaller than 1. The next step, sorry if I go in different way, in different direction, so is to derive your Einstein equation in the linearized case, okay? So I have linearized my metric perturbation. Now I want to compute my Einstein equation linearized, okay? So I need to start from my Christoffel symbol, okay? And I have d mu g rho nu plus d nu g rho mu minus d rho g mu nu, okay? If you plug your linearized metric here, so you will see that at the end, so what you will get, just to skip some steps, so you will have d mu h, yes, alpha nu, okay, plus d nu h alpha mu minus d alpha h mu nu plus some order h mu nu square, guys, okay? I want to linearize, so I stop at first order in h, okay? Then you compute your Riemann tensor, okay? Okay, so you just take the mu, okay, alpha mu beta minus d beta gamma alpha mu nu plus I already know that here I have terms that goes in this way, so I neglect them. So if you do all the computation, you will find something like 1/2 d mu d nu h alpha beta plus d beta d alpha h mu nu minus d nu d alpha h mu beta minus d beta d mu h alpha nu. Okay, so you continue, you all do all your derivation of the Ricci tensor, and you derive your Ricci tensor, your R mu nu, that is will be R alpha mu alpha nu, okay? And then you will derive your Ricci scalar, that will be R mu mu. That is what we need, if you want, not only, but there will be d alpha d beta h alpha beta minus box h, okay, where I have introduced this h, that is h alpha alpha, that is the trace of h, okay. And finally you have everything to compute your Einstein tensor, that is r mu nu minus 1/2 g mu nu r, okay. So if you have done everything properly, or if I have done everything properly, you should have okay. This is the quantity that you should obtain. What is the trick now? So the trick now is to introduce the trace reverse metric. Okay. So instead of working with the h, you work with what is called bar h, that is your h mu nu minus 1/2 is minus 1/2 yes, eta mu nu and the trace of h, okay. So it's called trace reverse metric, because if you compute the trace of h bar, this will be equal to minus h, okay. So, and if you rewrite your Einstein tensor in terms of the trace reverse metric, what you get is the following. Plus d alpha d mu h bar nu alpha minus. Okay, you should get this. So, of course, you have to realize that there are some terms that will be important for us, okay? So, of course, you have to apply your gauge transformation, okay, also to your trace reverse matrix that I defined right, okay? So, if you apply your gauge transformation to h bar, to the trace reverse matrix, so you will get something like this, h bar h mu nu plus psi mu nu, where this psi mu nu is equal to h mu nu d alpha psi alpha minus d mu psi nu minus d nu psi mu, okay? So now remember that we have a gauge freedom, right? Because we still have not used our gauge freedom, okay? So we can do a gauge choice to find our degrees of freedom, the physical degrees of freedom, because as I remember, as I told you, so gravitational waves are gauge invariant quantities. So this means that there are physical degrees of freedom. So if you look at this Einstein tensor, you can understand that the best choice, okay, is the following, okay. So, and okay, this is the best choice that we can make, because if we make this choice, these terms, and these terms goes to 0, and this was what Lorentz did, okay? So, okay, this is the Lorentz gauge that allows us to not completely, let's write almost, find the degrees of freedom. I will tell you later why almost. So you can also apply to the H. So if you apply to H, people call it as a Dead-Onder gauge, okay? So if you apply this gauge, okay, what you get is that, let me do this final thing, okay? The divergence of your linearized metric is the following, okay? And is 0 if and only if, so d mu h bar mu nu of x is equal to some function of x that respect this condition here, okay? So the derivation of this is a bit long. I skip a bit, but what is telling this is that even if you are fixing your Lorentz gauge, you still have some gauge freedom, okay? What is called the residual gauge freedom. Because you can always find a solution of this equation, so that the Lambertian is invertible, so you can always find a solution of this equation. So essentially, what you do, you fix also this gauge freedom, residual gauge freedom. So this means that besides the Lorentz gauge, okay, you fix this residual gauge freedom, and now that you have fixed both of them, you count your degrees of freedom. So if you count your degrees of freedom, so you start from your metric, okay, perturbation. So in principle, this is a 4x4 matrix. It should have 16 elements, okay? So this guy is symmetric, okay? So this means that, so for this matrix here, what you care about is just this part, because the upper part is the same. So they are 10, okay, in principle. So from the 16 you reduce to 10 since the matrix is symmetric. Then the Lorentz gauge allows you to subtract, to fix other 4 degrees of freedom, okay? And then you subtract other 2 with the residual gauge freedom. Okay? So at the end of the day, what you obtain is the number of physical degrees of freedom that are solution of your linearized equation. But if you have fixed the Lorentz gauge and the residual gauge, and you go and look at your Einstein tensor, so you realize that this guy is 0, this guy is 0, and this guy is 0, okay? So at the end, what you get is that your G mu nu is equal to minus 1/2 box H bar mu nu, okay? That is a wave equation, right? As soon as I write my Einstein equation, okay, G mu nu equal to 8 pi j 1/2 box H bar mu nu equal to 8 pi j t mu nu. Okay, so this will be now my Einstein equation after I have fixed on my gauge. As you can see, so if I am minus 1/2, right? Thanks. Yes, yes, you're right. If you don't have any source, let's put in the most simplistic case where this d mu nu is equal to 0. Later we will see how to extend this in curved space-time. So you have simply what we said at the beginning, that your gravitational waves respect a D'Alembert equation. That means that your gravitational waves propagates as waves in our universe, at least in flat space-time. Okay. So now, of course, you can also solve this with the t mu nu different from 0. Just to close, I think that I'm already out, right? Okay. So just to tell you that the most general solution of this will be the following: a wave solution, okay? H mu nu of x, that is d3k h bar mu nu of k e to the I k x plus h bar star h mu nu of k e to the I k x, okay? Where this k x is k mu x nu, okay? That is minus omega t plus k dot x, okay? That is essentially a wave solution. So we have shown that gravitational waves emerge naturally in linearized gravity, okay? So, and we have seen that this carries 2 degrees of freedom. As we will see, these are what are called the two polarization of the gravitational waves, H plus and H cross. We will see how to define them, starting from this. And at the end of the day, yes. So this we will extend this derivation in curved space-time, for instance, in a Friedmann-Lemaitre-Robertson-Walker, and we will see how to treat the source in curved space-time, because it's a bit complicated. Okay, so I would stop for today. So if you have questions, please ask. Which index? Here? This? No, it probably is an old stuff. Yes. Other questions? Background. If you want, yes. Okay, let me distinguish. It's a really stochastic. Yeah, that's true. Yeah. I will probably discuss at some point to distinguish the stochastic background. So you have to introduce some, how to say, features, okay, to allow to distinguish them. For instance, the simplest way is the frequency reconstruction that I told you before. So you expect some behavior in frequency for the astrophysical and for the cosmological one. The frequency is not enough, as we have seen, so you have to introduce other stuff. So one features could be the behavior, the anisotropic behavior of the stochastic background, because for instance, you expect that the astrophysical sources mainly reside in galaxies. So you expect a distribution that tracks essentially the distribution of galaxies, while in the cosmological case, you expect something that is more isotropic, right? This is one. Another thing is that the non-Gaussianities that if you want can use, and is strictly related to how this appears in the data stream, and you can relate this to the property of the noise in your data stream. So also this can help. In fact, so I will not touch this, but for Einstein telescope, where we will see more or less in 1 year 10 to the 5 sources, this is a big challenge to disentangle this kind of contribution from the noise. Yes. The other question was? Just this. Okay. Yeah. No, well, when I introduced the galactic binaries, you mean, okay? So essentially, this is the situation. So I didn't draw Lisa in 3D, okay? Let me, so you have the sun, you have the orbits, you have the Earth, Lisa will be here, okay? Is a triangle that is trailing the Earth on this heliocentric orbit, okay? So the point is, all these sources, essentially, so okay, all these galactic binaries are distributed on the disk of the galaxies. Okay, so as long as the satellites trail the Earth and goes around the sun, if you look in the data stream, of course, given the motion of the satellite and the fact that the Earth's there is the rotation, so you will see this that they will follow a distribution like this in time domain, if you want. And this is due to the fact that you are observing something that is all distributed on the galaxies. On top of these, there are some extra galactic sources, but the level of the background is not estimated yet. These are all galactic stuff. Yes. So it will be more clear when we will introduce the gauge invariants or gauge invariant quantity. So when we will extend this stuff to curved spacetime, or even if not curved spacetime, but just introducing these, the energy momentum tensor. So the behavior is different. So instead of fixing a gauge, you can also fix a gauge, but you build your so-called gauge invariant quantities. And you will see, and we will see, that all the scalar quantities or the gauge invariant scalar quantities, they don't, at least not in the Friedman-Robertson-Walker metric. So this will not follow a wave equation, while the Hij, okay, that is the only gauge invariant quantities that will respect a wave equation. Okay, we will do the extension. I was planning to do it today, but so, and you will see, coming back to your question, that building the gauge invariant quantities is much, if you want, that you don't need anymore to fix a gauge because everything is already, all the information are here. Okay, so is redundant to fix a gauge when you build these gauge invariant quantities. Okay, you can other choice. Other question? Okay, please. The ground base. Yeah. Okay, let me clarify this point. That probably was okay. So the ground-based detectors works in the let's say in the Hertz frequency band. Okay, so if you have ground-based as LIGO, Virgo, Cagra, and Telescope, Cosmic Explorer, so they work essentially from 1 Hertz to 10 to the 4 Hertz. Okay, and we saw what are the limitation due at 1 Hertz and what are the limitation 10 to the 4 Hertz. So if you look at cosmological sources with the CMB probe, you are probing other scales, okay? So you are probing, if you want, your frequency is directly related to the wavelengths, okay? So in the CMB case, okay, so you are probing frequency around 10 to minus 17 hertz, okay? So that is a completely different frequency band. Now, a cosmological background that comes from the early universe can appear both at CMB scales, but as we will see, it is everywhere at each scales, at each frequency if you want, but can also show up in the ground-based frequency band, okay? While, for instance, the astrophysical one cannot appear this because it is made by very close, as we have seen, very close sources, if you want, in terms of redshift. So you expect to see sources up to redshift 15. Okay, okay. The discussion is a bit more complicated, but so they are essentially close to us. While the CMB, as you know, is at redshift 1100. Okay. Okay, for the cosmological case, we have quite under control, so at least for the sources that we know, the shape, okay? The omega, yeah, the shape of the spectrum, so considering that this is LVK, advanced, or 5, if you want. So we have under control the shape. For the cosmological case, as I was saying, it's model dependent, okay? So let me anticipate something. So if you look at single field inflation, the easiest one, so and you compute in omega units your spectrum, so this will be a shape like this. This is again frequency, okay? Okay. So, but as we will see tomorrow, you can have way, for instance, with what I call extension of single field model that can increase your signal, okay? Imagine that they increase, but they do not have a similar shape. They have a shape like this, for instance, okay? Okay, so what we develop, for instance, are tools that take this frequency band, they bin this frequency band, they reconstruct band by band, assuming that this signal is a power law. Okay, so and you try to disentangle your cosmological sources with your astrophysical sources. It's obvious that so if you have an astrophysical background that is like this, but you have an astrophysical background that is like this, when you will compute your reconstruction error on your parameters, you will be quite degenerate. Okay, it will be hard. So, and then you have to be smart to find other ways to yeah, it's a superposition of sources. But the efforts in the community is taking these cosmological sources and build a template, if you want. So you know that, for instance, inflationary, let me call inflationary scenarios as some template. First order phase transition, they typically have, for the typical behavior of a phase transition, I will not touch this, but as a broken power law spectrum. So the cosmic strings has a shape like this, okay, for instance. So what you do, you try to do these efforts to distinguish your simple power law from the broken power law, from whatever you want to call this broken plus a bump, or you have some other sources that do like this. So this is the reason why the simplest tools to distinguish is the frequency shape. But of course you have thousands of, you can. What, sorry, with okay, so that's this is something that I will describe. So we are looking at frequencies, okay? Let's say from nanohertz, from 10 to minus 9, but even below. These are, okay, for people that are familiar with this plot here, okay? I will explain you more, okay? So here you have inflation, okay? From now on you have radiation domination, and then you have matter domination, okay? Of course, gravitational waves depends where they propagate, in which era they propagate. So at least all the frequency that I am discussing, that are related to gravitational waves interferometers are gravitational waves that then re-enter in the horizon all in radiation domination, okay? So what I will look at here are all gravitational waves that re-enter the horizon during radiation domination. Of course, if this is the matter part, you can also look at modes that re-enters in matter domination, okay? But we will see that the behavior of these, okay, it's a bit different, okay? Is this, for instance, one, okay? So I will not touch more this because it's, let's say, way far from the interferometers, let's say, area. Yeah, but yes, there is also this behavior here. Other questions? Coffee for everybody? Okay, let's go.